So, welcome back student to the next class of Introduction to Nonlinear Optics and Application. So, in this lecture number 14, we will going to learn two very important concepts. Last day we basically introduced that concept. So, optical rectification and linear electro-optic effects. So, both the effects are very important in application wise, but before going to the applications we need to understand basically what is going on, the physics behind that. So, in the previous class we understand in detail how the second harmonic is generated. So, just using a very simple equation which is scalar in nature. So, this scalar equation basically leads to a fact that when I launch an electric field of frequency omega into the system, then the nonlinear polarization can generate different terms. So, nonlinear polarization has different frequency component. One frequency component is omega, another frequency component was 2 omega, and another term was there in the nonlinear polarization term which does not carry any kind of frequency term. So, today we will going to understand what basically this term is and how it is affecting the system. So, this is called the optical rectification, we already mentioned. So, okay. So, this is the total picture what we will going to learn today. So, let me give you some review that this was our total polarization. P was equal to epsilon 0 chi 1 E plus epsilon 0 chi 2 E square. Now, E was represented in terms of complex quantity which is E 0 e to the power of I k z minus omega t, but we know that E is essentially a real quantity because electric field has to be real. So, that is why we just add complex quantity to make it real, and if I use this complex quantity a complex CC, that means complex conjugate term. So, this complex conjugate term basically add up with the main term. So, it gives rise to a real quantity, and this real quantity is nothing but E 0 cos k z minus omega t. So, when we use this electric field, the value of this electric field, my total electric field become this is my total electric field. So, last class we have already derived that. So, in this total electric field we find we have one frequency component omega, another frequency component 2 omega, and another term was sitting here without having any kind of frequency term. So, today we will going to understand what is the meaning of this term. So, here two figures are there, this is one figure and this is another figure. So, let us first try to understand this optical rectification, the schematic figure of optical rectification. So, in the first case we have the location of the dipole, the charges of the dipole, they are well separated, and now if I apply some kind of electric field, so what happened that this charge will now going to vibrate. So, this is some sort of a case, the first one is a case where the launched electric field should not have any kind of frequency component. So, now if we introduce some kind of frequency component, what happened, both the charge will now start vibrating, and there is a effective displacement from this position. If I now draw a line both the cases, you will find there is a effective displacement of both the charges. So, this effective displacement is basically due to this DC term. So, that means I am launching an electric field, this electric field is now has a frequency component. When this electric field has a frequency component, my polarization term, if I include the higher order effect E square having a frequency component 2 omega, and also one term which we call maybe the DC term, this DC term is there. So, on top of DC term we have a frequency component 2 omega. So, that means my dipoles are now going to vibrate. It will not going to vibrate, but also it is not just vibrate, but also the average location of the plus and minus charge will may also separate. So, this separation of the average charge is basically a term as optical rectification. Well, what happened if with this condition we launch an additional electric field from the outside. So, this is the linear electro-optic effect. That means, I am launching an electric field, this is a system and this system is nonlinear in nature. So, in the output I should have a frequency omega, a frequency 2 omega, optical rectification term is there, but on top of that we also launch an DC electric field on that. So, what happened by launching this DC electric field, the refractive index of the material is going to change because of this electric field. Here in optical rectification, only for this term where no external DC term is there, what happened that it will just change the separation, average separation of these things, but the refractive index is not going to change. But in linear electro-optic effect, what happened, there is a possibility that we can change the refractive index by launching the DC electric field outside. On top of that, I mean, I am launching electric field here, which is a frequency component E omega. On top of that, I am launching a DC field. So, we will going to discuss in detail in the next slide. Okay. So, these two phenomena we are going to understand by using the simple equation that we have already used in our previous class. So, optical rectification, as I mentioned, this is a DC term. So, this figure is already used in earlier lectures, that if I have a launching wave here with a frequency say omega, we should have a frequency omega and 2 omega, and when we have a frequency omega and 2 omega, that means the polarization should have a frequency component omega, a frequency component 2 omega, and also a frequency component or 0 frequency component or null frequency component, we write it P0. So, this is the equation essentially I am talking about. Here the total polarization is represented to 3 different parts. So, what happened here, the dipole will vibrating with the frequency omega. Here the dipole will vibrate to frequency 2 omega. Since it is vibrating with the frequency omega, it will generate a corresponding electric field of E omega, which is nothing but the fundamental electric field. It will start generating an electric field of 2 omega, which is the second harmonic wave or second harmonic field. But what happened here, let us understand, which we have already explained in the previous slide, that this is the dipole and the average location of the dipole will going to change slightly because of this DC term. So, if this is my plus minus, you can see that after applying the field, the location of the average location of the plus or average location of the minus charge is slightly changed, and this is basically the effect that is happening because of this optical rectification. Well, so after having this representation, this nice representation, we will like to understand mathematically exactly what is going on. So, in linear or electro-optic effect also we need to understand what is linear electro-optic effect. So, here basically in this slide we can see that when I launch an electric field E omega, when I launch an electric field E omega, which is this, and a DC field, which is basically, since it is a DC, it should not change with respect to time. So, that means it is nothing but a straight line kind of things or DC part. So, this plus this basically the total electric field plus DC, and if I go through the system where the polarization is represented by this term, then what happened in the outcome is refractive index change. So, the refractive index is going to change. This is a schematic representation of what is going on in electro-optic effect, so that you can understand readily what is the process. Okay. So, as I mentioned, now we need to understand this mathematically. So, now linear electro-optic effect means we are launching electric field from outside. So, that is why the electric field now not E omega plus DC, as I mentioned in the earlier slide. So, now it is DC, E DC plus E omega. E omega is a frequency component, is the electric field having the frequency component omega. So, it is nothing but E cos kz minus omega t. So, since it is E0 cos kz minus omega t, it is a real term, and EDC is also a real term, but the important thing is that EDC is not having any kind of frequency component, whereas it has a frequency component term omega. Now, the next thing is important, we need to make a square of that. So, when I make a square term, so E square, this E square is now here. So, that means I am making a square over this term. So, when I make a square over this term, what happened? We will have a square which is EDC plus b square which is this term, the square of this term, plus the coupling term, that means 2ab term. So, 2ab means 2 dc plus E0 cos kz minus omega t. So, 3 term is appearing because of the additional term of dc. Mind it, when I make a square term, because of the dc, one term should be here, that is for sure, but another term which is more important is here, this one. This term not only contained dc, but it coupled with the original electric field E0 cos kz minus omega t. So, that means if dc is there, the original field is coupled with that. So, this is independent term, but this is independent term, no dc is there, but there is a coupling term, and this coupling term basically give rise the linear electro-optic effect. And you can understand, you should realize that whenever you have a square kind of term, so this square kind of term basically if two terms are there, a plus b, and when I make a square of that, a plus b whole square, then a square plus b square, okay, naturally it is coming, but these two terms are not coupled, but 2ab term is also there and this is coupled. When 2ab term is there, things can happen. I mean, this coupling term basically gives rise to many important things. So, here in nonlinear optics we always find these kind of effects. So, let us go back to our slides. So, now what we will do, we just recollect all the term. So, EDC, I write EDC cos square kz minus omega t. I just want to reduce this square term. In order to do that, I just write 1 minus cos 2 theta with a half. So, this term also reduce, and the final we have the last term, and we just write the last term in simple way. So, now after having all the terms, what we will do, that we will again collect the term. So, when again collect the term means, let us go back to this. So, in the first part we have one electric field present here, and when I make E squared term, here also one electric field term E will going to appear. In E squared term, one electric field term E will going to appear. So, one can take common this E term both the cases. When you do that, then readily find that this coefficient will going to change because of this common fact. So, let us try to understand what exactly I try to mean here. So, this EDC epsilon 0, this term was there. In the previous case, there is a coupling term, and this coupling term basically this one, and now this basically our total electric field E, because my electric field was E omega plus E dc. So, I write this dc plus E omega means this term total electric field I write here. Then I take common all the terms which are not depend on the frequency. So, this is the term where E d square term is there, and E0 divided by 2 term is also there, because both the terms are not depends on frequency. So, this is the term where we have no dependence, no frequency dependence, and then we have one term where the frequency is 2 omega. If you see carefully, the frequency term is 2 omega, which is naturally come because we are making square of that thing, we are making E square. And finally, as I mentioned, we have a coupling term E0 cos kz minus omega t multiplied by E dc. So, if I write this term, you will find one can write is that E0 epsilon 0 chi 2 E dc multiplied by E. So, this is a term which will going to have some effect. Okay. After having all this term, now again we start recollecting one by one. So, let us see what happened for the first term. The first term we have epsilon 0 chi 1 E dc. This term again should not have any kind of frequency component. Since this term has no frequency component, I can correlate this term with this one. Again, this term is something which does not have any frequency component. So, we gather all these term and we call these things as term 1 as written here. This is my term 1. So, the first term which does not have any frequency component, I can write P 0. Mind it, in the previous case when we were try to find out what is going on and try to find out what was P 0, in that case, in the previous case, our P 0 was simply epsilon 0 chi 2 E square divided by 2, that was my P 0 in the previous case. But here, as soon as I add another term EDC to my total electric field from the outside, I have 2 EDC term here, which also does not have any kind of frequency component. So, the important thing one should remember that for this linear electro-optic effect, the optical rectification term is also modified. So, here the optical rectification term in the previous case was this, but here by applying the additional DC electric field, it is now increased, and this increase thing is coming, the increased value of optical rectification term is coming because we are launching the DC electric field from the outside, which is quite natural. Okay. That was the first term. What about the second term? The second term, we will recollect all the term having the value E 0 cos k z omega t, that means having the value E omega. So, EDC, this term I take common, this term I take out, this term I take out. So, next term is epsilon 0 chi 1 E 0 cos k z omega t. So, and another term is here E 0 cos k z omega t, but the coefficient is different here, epsilon 0 chi 2 E 0 DC. So, epsilon 0 is common both the cases. So, I write epsilon 0 here. In this case, it is chi 1, and in this case it is chi 2 EDC, and there is a 2. So, I do that, and next term E 0 cos k z omega t and E 0 cos k z omega t, both are same. So, I take it common. E 0 cos k omega t is a common, and then we will have one important term here as a coefficient in second in set of this 2 equation. I mean this if I write this is a 2 number 2 term in P. So, we have a different kind of coefficient in front of this, and finally, we have a term which was already there in the previous case, which is basically the second harmonic generation term having the frequency component 2 omega. So, that term is already there in the previous case, and for linear electro-optic effect, when we launch the electric field, DC electric field outside, this term is also there. So, when we have these 3 terms, the first term is basically the optical rectification, modified optical rectification. Term 2 is also modified because of the electric field, and it is related to the fundamental field E omega, and the next term is second harmonic generation. Okay. After having all these 3 terms, now we can understand that my coefficient is changed. So, now if I write as I mentioned in the previous case that my P 0 term is now modified, which is a rectification term, and now I write here, if I go back to the previous slide, my two term, second term, I have a coefficient here. In the second term, I have a coefficient here. This coefficient, now I write chi effective. So, effective means now instead of having susceptibility chi 1, I have chi 1 plus chi 2 with the additional EDC term with multiplication of that thing. So, this combination we call chi effective. So, this chi effective basically now a new susceptibility, linear susceptibility term. So, this new linear susceptibility term is basically a term which change the refractive index. So, now we write here chi effect. Now we write here chi effective, all the 3 terms, this is the second harmonic term as it is, the P0 term is as I mentioned the modified optical rectification term, but here the most important term is the second one. So, second one term is now modified with chi effective. So, chi effective, now this is P omega is E omega, that means this is a linear relationship. So, linear part of the polarization basically give rise to the refractive index, linear part of the refractive index. Now, inside the refractive index we know that susceptibility is related to the refractive index, because n is 1 plus chi 1 whole to the power root over of that. So, that means refractive index is directly related to the susceptibility. After applying the DC electric field, what happened here, that my susceptibility term is now modified by this effective susceptibility. So, since it is modified the effective susceptibility, I should write my n from this equation like root over of 1 minus susceptibility root over of effective. So, this E effective is now become a new term as I mentioned, which change the refractive index. If I write n, then I should write here n effective. So, effective refractive index is going to change here because of the application of the DC electric field. So, if I now write the whatever I mentioned, if I write carefully, then we will find that P omega, as I mentioned, P omega, which is epsilon 0 chi effective E omega, which is a new term that is appearing because of this DC effect. So, effective susceptibility can be represented by this. Chi 1 is a fundamental susceptibility or the first order susceptibility. On top of that, we have one addition term E DC into susceptibility multiplied by chi 2. So, these two terms basically these two terms, if I combine together, we have an effective susceptibility. Now, after having this effective susceptibility, if I try to understand what is my refractive index. So, my refractive index is nothing but 1 plus susceptibility effective. So, this susceptibility effective, if I write, I should write in this way. So, this additional term is basically responsible for the change of the refractive index. So, that means I can change the refractive index. The beauty of this term is that I can change my refractive index, but in order to change the refractive index, either EDC or chi 2 both has to be non-zero. If EDC is not there, that means if I not launch any kind of DC field, then this term is not there. That means we will not going to change my refractive index. So, that means EDC is an important thing, but it is not always that EDC is there. You can see that the susceptibility, second order susceptibility is also sitting here. So, if chi 2 is 0 in one case, say some cases chi 2 is 0 or very close to 0, or the material is not nonlinear at all, then also this term will going to vanish. That means, if I have a material where we have chi 2 nearly equal to 0, if I launch the electric field with a DC electric field, then obviously the second harmonic will not going to generate, that is for sure, that the second harmonic will not going to generate, but at the same time the linear electro-optic effect is not also going to generate, as per the equation suggests that chi 2 is 0. So, this term again will going to vanish, and if this term is not there, we will not going to have any kind of effect, susceptibility, any kind of effect here. So, today we will we have learned very important concept, two very important concept. One is optical rectification, and optical rectification is nothing but if I launch an electric field in a nonlinear medium having second order susceptibility, then one DC term will appear automatically that basically change the average displacement of the dipole which is already vibrating, and this basically rectify this thing, optically rectify the thing, but does not change the refractive index. On the other hand, if I launch an electric field from the outside with my fundamental field, then what happened that because of this nonlinear interaction, due to the application of this external DC field, the refractive index will going to change, which is called the linear electro-optic effect. So, with that note, let me conclude here. So, thank you for your attention. So, in the next class, we will discuss more on the frequency mixing. So, with that note, let me finish here. Thank you for your attention. So, see you in the next class.